Now let's use the stationary functional approach to derive the finite element model of a bar. For a bar tensile problem, a bar tensile problem, the total energy of the structure would be given by the elastic energy stored in the structure minus the external work done minus the work done by the externally applied force. So here you are. This is the externally applied force multiplied by the deflection at any point. So force times deflection, that's the external work. And for the integration of the stress times the strain, let's remember that the strain of a bar is given by the rate of change of deflection with respect to x. So this is actually epsilon. And the stress is given by the modulus of elasticity times the strain. So that's why we get the strain squared here, or partial u by partial x all squared. And since everything is independent of y and z, the integration becomes the integration over x the integration over the bar length. So it's reduced from a volume integral to a line integral over x. So here what you see here now is just the modulus of elasticity times the cross-section area. Both are still included in the integral because they may vary over the length of the bar. However, our example here, we will just say that they are constant. And the deflection, of course, is the function of interest. This is the function that we want to find. We don't know what u is, but that's why. So now we can say that pi is a functional of the deflection function. Okay, I hope this is now clear for all of us. Now, taking the variation, the first variation of the total energy, we'll find that the variation operates on the functions of interest over u here. See, so if you differentiate this g of u, you'll get twice partial u by partial x multiplied by the variation of partial u by partial x. And the mathematicians of the variational method said that the variation of the differentiation is differentiation of the variation. So we can just here say that this is partial by partial x times the variation of u. Okay, so if this is the case, we can apply the integration by parts on this term, which gives us the boundary term that we have here minus the integration of the variation of u multiplied by the second derivative. So the integration by parts just moved the first derivative from one of the terms and moved it to the other. We used it here just to move it from the variation of u in order to have the variation of u explicitly available for us here to take it out as a common factor. Let's focus for a minute on the boundary term that we got. Here the boundary term says that the variation of u multiplied by the strain at x equals 0 should be equal to 0, which is what we know physically from the boundary conditions of a bar. It's either that you define the deflection of the bar at a point to be equal to 0, which is the fixed boundary condition of a bar, or that it's a free boundary condition in which the strain is equal to 0, so partial u by partial x is 0. So one of these should be equal to 0 in order for this term to be satisfied and to be equal to 0 and to be dropped. If it's not equal to 0, that's to say, if we have a load, then then EA partial u by partial x would be equal to the load, or the deflection would be defined as a given value at that point. Okay, now let's regain the focus to, let's direct our focus to the main integration. If the integration is equal to 0, then the integrand should be equal to 0. That's what mathematicians taught us in integration. So we would say that the variation of u multiplied by this bracket is equal to 0. Since the variation is an arbitrary function, we don't really know it, and we don't care much about what its value is. So we end up with saying that EA times the second derivative of u plus f is equal to 0, which is the original differential equation that described the bar. What I wanted to show here is that starting from the energy, I could get to the differential equation together with the boundary conditions. However, for finite element analysis purposes, we are not really interested in the differential equation, because if we have the differential equation, we would use weighted residual methods. But I wanted to show the link here. If we start from the energy, we can end up with the differential equation. If we started with the differential equation, we can go all the way back to the energy terms. Okay, so now let's focus on what we call the weak form. Let's focus on what we call the weak form of the problem, which we see here. It's the variation, the first variation of the total energy. We will use this term to derive our finite element model by using the shape functions into the integration and follow a very simple, straightforward procedure. Okay, now we're going to use the weak form that we derived in the previous video together with the shape functions that we use in the finite element model and the variation of the function. Here, the variation of the function would be the variation of, the variation of the displacement would be the variation of the nodal deflections. Since n of x is determinant, I know n of x, it's something that I already know, I put it by myself into the model. So the variation of the deflection u of x is actually the variation of the nodal deflection. Remember here, these are u1 and u2, the nodal deflection at the ends, both ends of the bar. Let's use u and the variation of u into the weak form. Here, I removed variation of u and u and replaced them with the interpolation functions or the shape functions multiplied by the nodal deflections. Here, the integration includes the variation of the nodal deflections, which are independent of the integration, independent of x. So we can get them outside the integration. And the variation methods say that the variation of pi should be equal to 0, which makes it a stationary functional. And that actually gives us that this integration is what equals to 0, since the variation cannot be equal to 0 by itself. So using this integration and equating it by 0, we end up with the original element equation of the bar. Here you see the integration of nx as a column vector multiplied by nx as a row vector, exactly what we did using the weighted residual method. So this whole integration will give us the EA over L 1 minus 1 minus 1 1 matrix, the K matrix, the famous bar stiffness matrix, and the integration of the shape functions multiplied by the externally applied load will give us the generalized force terms. I will not get now again into how to assemble and solve and apply boundary conditions and solve. Now we just have K times U equals F. That's the element equation. We'll go back to the normal finite element procedure, assemble equations, apply boundary conditions, and then solve for the unknown variables U, which are the nodal deflections.